Welcome to my presentation about the main benefits of potassium nitrate over potassium chloride, potassium sulfate and potassium thiosulfate. Let me be very clear. Sulfate is an essential plant nutrient. So this presentation is not against sulfate. In fact, SQM has been a producer for many years of potassium sulfate. But potassium sulfate is to be used in the first place as a sulfate containing fertilizer. And it has to be added just to supply the required amount of sulfate for proper plant functioning. If we look, for example, in this example at the sulfate export of an orange fruit that comes together with the potassium, you can see that the orange fruit has a ratio of 1 unit of potassium expressed as K2O and 0.04 of S as elemental sulfate. If we look at supplying all the potassium with potassium sulfate, then this ratio increases to 1 to 0.34. So it's 8 times more than the plant requires. And if compared with potassium sulfate, it's even double. It's a ratio 1 potassium to 15 sulfate applied as thiosulfate. This excess of sulfate, and that is the point I want to make, the excess of sulfate will stay in the soil and in time will contribute to increased soil salinity. Furthermore, there is a risk of fixation of calcium sulfate. Calcium sulfate is soluble in water, but only to a small extent. Potassium nitrate is fully compatible with other fertilizers in most agrochemicals, whereas potassium sulfate can get fixed together with calcium to produce gypsum. And gypsum is hardly soluble in water. There's a small solubility of gypsum, only 2 grams per liter, but under dry soil conditions, calcium will associate with sulfur and produce a precipitate called gypsum. So all this sulfur, or it contributes to salinity, or it will also block the availability of calcium due to the formation of gypsum. Potassium nitrate has a higher solubility and faster dissolution rate than potassium sulfate. And we try to visualize this in 2 ways. The first one is showing what will be the speed of dissolution when potassium nitrate and 2 times the potassium sulfate are being placed on a wet sponge. And this wet sponge is covered by a tissue paper which also gets moist because of the capillary functioning of the sponge. If we look at the slide on the right with the green coverage, we see 3 rows. The first row is our crop KS, SQM's prilled potassium nitrate. The second row is a granular SOP, and the third row is a prilled SOP as it's being produced in Egypt. We thought that maybe the prill, compared to a granular is more compact, but also a prill could have a faster rate of dissolution. And that's why we included the prilled potassium sulfate in this test. This is the starting point on the first day of the comparison. On top, our crop KS, our potassium nitrate. The second one, the granular SOP, and the third one, the prilled SOP. If we look after 3 days, we see that in the case of potassium nitrate, already part of the prill started dissolving. After 4 days, only a few particles are being less, and after 6 days, only a typical residue is left behind, but the prilled potassium nitrate, in comparison with potassium sulfate, both the granular and the prilled shape clearly show that even after 6 days being under this condition, hardly any dissolution took place. So this clearly shows why potassium nitrate dissolves faster than potassium sulfate. Now, for those who are really interested in the detail, I will give you the 2 reasons why this is happening. Why does potassium sulfate dissolve so slowly? But first, I will show you a second example, and this is a video made by our colleagues in the United States that shows you in a time-lapse video in 30 days the same principle, but much nicer, that potassium nitrate dissolves in its prilled form much faster than potassium sulfate. I will now start this video. Now you've seen this video and also the information I showed on the wet sponge with the moist surface. So what could be the scientific reasons for this difference in speed of dissolution between potassium nitrate and potassium sulfate? The first reason is shown on this graph, and it clearly shows that the maximum solubility of potassium nitrate, in particular at higher temperatures like 20 degrees Celsius, can be 3 times or more compared to potassium sulfate. But the second reason is equally important. Potassium nitrate has a greater difference in vapor pressure between pure water and the saturated fertilizer solution than potassium sulfate. If we look at the graph on the screen, you can see that on the left side, at a temperature of 10 degrees Celsius, this difference in vapor pressure between pure water and a saturated potassium sulfate solution is 0.15, where in the case of potassium nitrate it's 0.35. So it's, in the case of potassium nitrate, it's 2.5 times higher than potassium sulfate. If the temperature gets up to 20 degrees Celsius, this difference between SOP and potassium nitrate becomes a factor 5. It's even larger, and that is all related to the difference in vapor pressure between the saturated fertilizer solution on the one hand and pure water on the other. What we've seen recently is many companies use salt index to explain differences between potassium sulfate and potassium nitrate. Salt index is already an old concept that was developed in the 40s of the last century and is mainly used to show the safety of putting a fertilizer at a developing seed in emerging roots, if there would be any risk of burning the roots or not, based on the salinity index of a certain fertilizer. So the salinity index allows to compare fertilizer with each other for this specific characteristic. The authors of a scientific paper, Murray and Klepp in 2004, already indicated that the current fertilizer salt index tables are misleading. And to better understand, you have to know that there are 2 methods being used to calculate the salt index. The first one was developed by Rader et al. In 1943, and they looked at salt solution osmotic pressure. I will explain in a second how this method was developed. And the second one was developed 15 years later by Jackson et al. In 1958, which based themselves on a method called electrical conductance. This is a method we still use until today in hydroponics to measure the salt content in a nutrient solution as it goes to the plant. Let's start with the first method. It's a complicated method involving various steps in order to come to the final salt index. What these authors do? They started mixing a fertilizer with air-dried Norfolk salt. And then they watered this mixture until 75% of the maximum moisture holding capacity was reached. They left the solution stand for 5 days, after which the salt solution was subtracted from this mixture. This salt solution was analyzed for the freezing point. And to understand and interpret this freezing point, they looked at the freezing point lowering temperatures, which then were converted to osmotic pressure by using tables that were developed for vegetable subs. And from here, the salt index was developed as a relative term compared to the increase in osmotic pressure of sodium nitrate compared to the increase in osmotic pressure of the specific fertilizer being tested here. So as you can see, a number of steps were involved to derive, based on tables from vegetable steps, to a certain salt index value. The second method was based on electrical conductance, a much more simple laboratory test. And here the salt index was measured by electrical conductance, which is much easier than using the osmotic pressure. What did the authors do? They took again the electrical conductance of 0.1% of sodium nitrate solution. This was the standard. They dissolved 1 gram of sodium nitrate in a liter of water, laboratory quality water, chemically pure water, and compared this with the EC value of the fertilizer under similar conditions. And then they divided the EC value of the fertilizer we were interested in by the EC value of sodium nitrate. So it's a much more easy way of testing the salt index. Now let me compare the salt index of the two methods. On the left side you will each time see the salt index developed by the method of Rader, and on the right side the one based on electrical conductivity from Jackson et al. If we compare the salt index by Rader, we can see that in the case of potassium sulfate it has a value of 46, and in the case of potassium nitrate a value of 74. Now if we compare with Jackson, the picture changes. Now it's clear that in the case of potassium sulfate the value is 111, whereas in the case of potassium nitrate it's 98. So depending on the method that has been chosen, on the left side you see potassium sulfate has a lower value, on the right side you see potassium nitrate has a lower value. And our preference is based on the one on the right side, the Jackson method, which is the current standard. I believe the Rader method is only used for commercial reasons, but it's an outdated method not being used anymore these days. There are different ways to express the salt index. Another way is using what they call the partial salt index, where they divide the salt index by the units of potassium of the fertilizer. Again, if we look at the left side, the Rader method, in the case of potassium sulfate, a value of 0.9, compared to potassium nitrate, a value of 1.6. But with the Jackson method, on the right side you can see that the picture is equal. We have similar values for potassium sulfate and potassium nitrate, both present a partial salt index of 2.2. Another way of expressing the partial salt index is by expressing it by the total of macronutrients, the percentage of nitrates in the fertilizer plus the percentage of phosphate plus the percentage of K2O. That would result again with the Rader method on the left side, a value of 0.9 for potassium sulfate still being lower than the 1.2 of potassium nitrate. But now, again, if we look at the Jackson method, and with this partial salt index we also include the nitrate content of potassium nitrate in the equation, you can see that again potassium nitrate has a lower partial salt index based on the sum of the percentage nitrogen, phosphate and potassium. Now let's go back to the EC method that's being used in hydroponics. In all the reference tables today you can see that for potassium sulfate it's indicated the value of 1.54 measured under standard condition, which means the dissolution of 1 gram of potassium sulfate per liter of water at a temperature of 25 degrees Celsius, and the one for potassium nitrate is 1.35. So what can we conclude if we compare the various salt index references and the EC levels? First of all, the current method is the EC method, the electrical conductance. The Rader method is not being used anymore, it's very laborious and it's outdated. Secondly, if we use the Jackson method, the newer method, we can see that potassium nitrate always have the lower value when we just compare the salt index, the partial salt index or the EC level. So in fact, when it comes to, as it's being used many times, the impact on salinity, potassium nitrate has the lower impact compared to potassium sulfate. But in the end, what is the practical value of the salt index? I think it's very limited, because it's not about the salt index, but it's about the residual nutrient level. With potassium nitrate, all the potassium and all the nitrate is being absorbed by the plant. Nothing is left behind in the rooting zone, so there is no impact on salinity built up in time. If we take potassium sulfate, again, all the potassium is being absorbed when we applied equal levels of potassium and nitrogen, as is the case with potassium nitrate. But most of the sulfate will stay behind in the soil. And this sulfate that stays behind in the soil will accumulate in time and will impact negatively soil salinity. The soils become more saline over time when continuously potassium sulfate is used for feeding the plant with all the potassium instead of limiting the sulfate input to the sulfate demand of the crop. Another way of expressing the impact of salinity in EC is to compare the relative EC values. In this figure I've put the EC value of potassium nitrate at a relative number of 100. Now, if I want to give the same amount of potassium and the same amount of nitrogen with potassium sulfate, then I could replace or I could include the nitrogen source in the form of ammonium nitrate or as ammonium sulfate. Now look what's happening. Potassium nitrate, a relative EC level of 100, and now we start replacing all the K with potassium sulfate and all the nitrogen with ammonium nitrate at equal levels of K and N. Then the figure is showing that the EC on a relative scale is already increasing from 100 to 146, an increase of almost 50%. And it even gets worse when we start replacing the nitrogen source by ammonium sulfate. Then it goes up to 192, which means an increase in salinity impact of 92% compared to potassium nitrate. In certain areas in the world, one could argue what would happen if not ammonium nitrate or ammonium sulfate is being used, but just urea, because we know that urea has an EC level of more or less 0. Only some impurities can contribute to certain EC, but in practical terms we can consider EC level being 0. So what would happen if I have a combination of potassium sulfate with urea? Well, in fact this urea will not stay urea forever. It will get transformed first in the process of hydrolysis, where it becomes ammonia NH3, which in the chemical process and bacterial activity which is called ammonification, is converted to ammonium. And then again we're in a similar situation as shown with ammonium sulfate. So it's just a delay factor in time, but sooner or later urea gets transformed into an ammonium source, and then consequently also the EC will increase again. There's also a different way of showing the main advantage of potassium nitrate over potassium sulfate. And that is just to show you that indeed potassium nitrate is a well-balanced source of nitrogen and potassium. I took an average of the recommendations used in hydroponics of tomato, sweet pepper, melon and cucumber. And that is shown on the screen. You see on the x-axis ammonium, nitrate, potassium and sulfate, and on the y-axis their levels, the recommended levels in the standard nutrient solution expressed in ppm. Now let's assume that all the potassium will be applied through potassium nitrate. Well, in fact it's almost all, because part of the potassium in the recommendation is applied through MKP, monopotassium phosphate, and a small proportion through SOP. But for the remainder I can supply all the potassium with potassium nitrate, and at the same time I'm supplying part of the nitrate nitrogen demand. What is remaining will be supplied with calcium nitrate. In this program you can see that the ratio ammonium nitrogen to nitrate nitrogen is 7% of ammonium nitrogen and 93% of nitrate nitrogen. Now let's do the same exercise by using potassium sulfate as the main K source. Again, some of the K is supplied by ammonium potassium phosphate, but now the remainder will be fully supplied by potassium sulfate. In this case, we will supply excess of sulfur as sulfate. Part will be supplied by SOP from the standard recommendation and magnesium sulfate, but you can see that on top of the recommendation there will be an excess of sulfate. And this is undesirable because excess of sulfate will lead to salinization. But the second impact is that with potassium sulfate we are not supplying any nitrate nitrogen anymore, as we did with potassium nitrate. So that means there's a gap in the nitrate nitrogen balance. And this gap most probably will be supplied with ammonium or with urea. I just put urea in the example, but you can see that urea, as shown before, will be transformed rapidly into ammonium, so indirectly it's a source of ammonium nitrogen. If we look now at this ratio, we can see that the balance is more equal between nitrate and ammonium. But that is not the desirable situation in hydroponics. Excess ammonium starts competing for the uptake with calcium. The plant will suffer from calcium deficiency, and this will result in blossom end rot. The picture shows you blossom end rot in watermelon, but a similar effect can be shown in pepper, sweet pepper, but also in tomato. And if we look at the balance, remember, in case potassium nitrate was the main K source, it was 7% ammonium to 93 of nitrate. Now, if you look at the bottom of the slide, it's 42% of ammonium to 58 of nitrate. So it's a big change in the nitrogen source just because of the selection of the potassium source. And remember, at the same time, if we supply all the case potassium sulfate, there also will be an excess of sulfate. To summarize what we saw with potassium chloride, in chloride sensitive crops, avoid chlorine containing fertilizers, and when it comes to salinity, stay away from potassium sulfate or potassium thiosulfate. Again, we are not against potassium sulfate for the sulfate, but any excess of sulfate, as any excess of chloride, is undesirable and will disturb ideal nutrient balances for plant uptake. And this excess of sulfate and chloride will be in particular cause for doubt when it comes to growing under saline conditions or dry conditions, because there the salinity impact will be more visible when it comes to plant performance. So we already deleted potassium chloride from the equation, and now we can also delete potassium sulfate and potassium thiosulfate for the sulfate content from the equation. Thank you very much for your attention. It was great being here with you today, and I hope you can use all this information for the benefit of the crop. Thank you again.